Hello students, in last video we have seen what are the expression for torque and potential energy of a dipole when it is placed in uniform electric field. Today we will see what happens if the dipole is placed in non-uniform electric field, and we will also solve some examples based on uniform electric field. Okay? Dipole placed in non-uniform electric field. Okay. How non-uniform electric field is represented, that we studied in electric field lines. Suppose if the electric field lines are not equidistant lines, these lines are like this. One side they are closer to each other, one side they are far away from each other. If they are like this, then this will represent a non-uniform electric field. Okay, this is the direction of the field, but this field is not uniform. Okay, if field lines, when they are closer to each other, here the crowding of lines will be more. If crowding of lines is more, means this will be called as, or this is strong field region where crowding of electric lines of force is more. Where crowding is less, this we call it as weak field region. Okay, if in this field, which is not uniform, if we place electric dipole, then we can place electric dipole in two ways. This is the direction of the field. If I place the dipole in non-uniform electric field, if I place dipole like this, dipole is placed in non-uniform electric field, such that dipole moment is parallel to electric field. See, this side it is strong field region, this side it is weak field region. We will place the dipole like this. This is minus q, this is plus q. It is the direction of dipole moment will be from minus to plus. This is the direction of dipole moment. And this side is also the direction of electric field. That means dipole moment is parallel to electric field. Like this we represent this. Dipole moment is parallel to electric field. If dipole moment is parallel to electric field, then what happens? You see, suppose if the dipole is placed like this, this is minus q, this is plus q, and this is the direction of dipole moment. Then what happens inside the dipole? The dipole will exert force on both the charges. The electric field will exert force on the both charges. On this negative charge, see, this is the direction of the field. That means this side should be plus This side it should be minus. Electric field direction will be from plus to minus. This negative charge will experience a force in this direction towards, see, this is minus, this is positive plate, this is negative plate. Direction of electric field is from plus to minus, but it is not uniform. If this is the direction of electric field, this minus Q will experience a force of, here, see, I told you this field is not uniform. That means, let us say the strength of electric field here is E1 and the strength of electric field in this region is E2. I am telling you, this is strong field region, this is weak field region. That means the magnitude of E1 will be more than the magnitude of E2. This negative charge will experience a force in this direction and this positive charge will be pulled in this direction by different forces or same forces? By different forces. See, what is the force expression? Formula for force is Q into E. But here E is different, here E is different. This E is more than this E. That means on this will get a net force or F1. So this is F1, force on negative charge in this direction, and this will be F2, force on positive direction in this direction. What is F1 is equal to? F1 is equal to this minus Q into E1. Then F2 is equal to, charges are same in magnitudes, this will be Q into E2. Since E2 is more than E1, F1 will be more than F2. Since E1 is more than E2, E1 is more than E2, F1 will be more than F2. E1 is more, E2 is less, F1 will be more than F2. F1 is more than F2 means net force will be acting in this direction. This is more than this. That means net force acts towards left or right. Net force acts towards left side. It means left side, which field is there? Strong field region. And right side, weak field region is there. If net force is acting in this direction, then the dipole will move in this direction. What I mean is, dipole will move in this direction means dipole is moving towards weak field region or strong field region. It is moving towards strong field region. Therefore, when P is parallel to E, what I considered here is P is parallel to E, then net force will act towards left. That means dipole moves towards strong field region. Dipole moves towards strong field region because net force is acting in this direction. And overall meaning is, if I place dipole such that dipole moment is parallel to electric field, then the dipole will experience a force towards left. Therefore, I can say that dipole is moving towards strong field region. That means if dipole is placed in such a way that P is parallel to E, it moves towards strong field region. That means it is showing or it is executing translatory motion. Because of the torque, if you place it by making some angle with electric field, it will experience torque anyway. It will experience torque as well as it is moving in one direction. That means it is also showing translatory motion. Rotational motion will be due to torque and translatory motion is due to net force. Suppose if the field is uniform, what is the net force? Net force will be 0. This side also it is E, this side also E, net force will be 0. Dipole will not move in either of the direction. Then we can say that it can rotate. Only it can rotate under the influence of torque. Translatory motion is not possible. Here torque will be also acting on the dipole and net force will be also acting on the dipole. That means due to net force the dipole will show translatory motion. Okay, if I place the dipole in the reverse manner, reverse manner means if P is anti-parallel to E, okay, note it. So when it is placed such a way that P is parallel to E, it moves towards which field region? Strong field region. Okay, this is first case. Note it. Then if you observe the second case, what is the second case is dipole is placed in non-uniform electric field such that its dipole moment is anti-parallel to electric field. Anti-parallel to electric field means I will show it like this. If it is parallel, both arrow mark you can put in only one direction, anti-parallel in opposite direction. Okay. If it is placed in opposite direction like this, see here only I will take, this will be plus Q, this will be minus Q. This is my dipole moment. Okay. Dipole moment will be from minus to plus. Dipole moment is now, it has become anti-parallel to electric field in this direction. Now you say, see, if this is plus, then a F1 force will act on this charge in this direction and a F2 force will act on this charge in this direction. Negative charge will be pulled towards positive plate, positive charge will be to pull towards negative plate. This is F1 force, this is F2 force. Now you see, this I make it as plus, this I will make it as minus. Then on this charge same force F1 will act, but now what is the direction of F1 you see? This F1 is now acting on which charge? It is acting on positive charge. So the direction of F1 will be like this, because positive charge is pulled towards negative plate. Then negative charge will be attracted towards positive plate. Then F2 will be acting in this direction like this. Now also F1 and F2 value will be same. F2 is equal to, again it is Q into E2. Now which field is strong? E1 is strong, then E2. Since, again, then right, since E1 is more than E2, F1 is more than F2. That means F1 is acting in this direction. In this direction, if it is 10 Newton force, in this direction it will be 4 Newton or 6 Newton force. That means F1 is more than F2 means net force now will act in this direction. Net force acts towards right. Net force acts towards right. That means dipole is ready to move in which direction? Ready to move in this direction. That means it is moving towards weak field region or strong field region. Therefore, when I can say when P is anti-parallel to E, P is anti-parallel to E, I can say dipole moves towards right because of the net force. Dipole moves towards strong field region. Okay, these are the two cases we'll understand. Follow this. This is F1 now, this is F2. F1 is more, F2 is less. Then dipole moves towards right. Towards right means it is weak field region or strong field region. It moves towards weak field region. Okay. When P is parallel to E, it moves towards strong field region. When P is anti-parallel to E, it moves towards weak field region. What is the net force acting on the dipole? It is F1 minus F2 in both the cases. Okay. Follow this. Now we'll move. That means what I can say is, you write this, when P is parallel to E, dipole moves towards strong field region, and when P is, I will take this like this, opposite arrow marks, it indicates it is anti-parallel. Anti-parallel to E, dipole moves towards weak field region. Make a note of this point. Okay. When it is parallel, strong field, it will move towards left. When it is anti-parallel, it moves towards right. Okay. What is the net force acting on the dipole? It is F1 minus F2. In both the cases, it is F1, it is F2. This is more, this is less. That means net force acting on the dipole is F1 minus F2. That means clearly it indicates dipole is exhibiting translatory motion under straight line motion. Moving towards right or left is translatory motion. Rotating under the influence of torque is rotational motion. That means it is executing both types of motion. If it makes some angle, then that means that is a dipole placed in, this is point number 1, point number 2 you write, this is point number 2, a dipole which is placed in non-uniform electric field. An electric dipole placed in non-uniform electric field it experiences both torque and net force. A dipole placed in uniform electric field will experience only torque, but net force is 0. A dipole which is placed in non-uniform electric field will experience both torque and net force. That is, dipole undergoes both rotational motion and translatory motion. Translatory motion means straight line motion, moving towards one side. It will experience both torque and net force, and because of torque it will undergo rotational motion, and because of net force it will undergo translatory motion. The same case, if you are riding in uniform electric field, a dipole placed in uniform electric field experiences only torque but no net force. Therefore, dipole shows only rotational motion but not translatory motion. Follow this? Okay. Then, what is the net force acting? I told, in this direction it will be, if it is negative like this will be F1. In this direction, if it is F2. If it is plus, this is F1, this is F2. In both the cases, what is the net force acting? Since F1 is more than F2, net force will be F1 minus F2. Okay. Now let us see. What is the net force? This is third point, you can say, take it as a note. Net force will be, let us write, it is F. F net is equal to F1 minus F2. That means F is equal to, what is this? F1 means what? Q1 into E. So Q into E1 minus, this is Q into E2. This net force is equal to Q comma, Q bracket you can take outside, E1 minus E2. Okay? If you want to express it in terms of dipole moment, if I suppose that length of this dipole, see, this is minus Q, this is plus Q. If I say that this length is L, then what is dipole moment? Dipole moment is equal to any one charge multiplied by length. I can take it as 2A also. Conventionally we took 2A while deriving the expression for electric fields. Then if you multiply this equation by Q, multiply and divide by L, E1 minus E2 divided by L. Q into L gives what? Dipole moment. F is equal to dipole moment into E1 minus E2 by L. This E1 minus E2, nothing but I can take it as delta E, change in electric field while moving from this point to this point with distance. Change in electric field with distance. Okay? F is equal to, I can write this is P, this is change in electric field with respect to some distance. This quantity, change in electric field with distance, if suppose any quantity changing with, in physics, if I suppose at this velocity changing with time, how I will read this? Rate of change in velocity. If a quantity is changing with respect to distance, change of any quantity with distance, change of any quantity with rate is called as, with time is called as rate of velocity. Here we call it as change in electric field with distance. If some quantity is changing with distance, then we call it as gradient. Change in velocity with distance, it is called velocity gradient. Change in velocity, change in temperature with distance with respect to length, then it is called as temperature gradient. Now here it is the gradient of electric field. So this is the net force acting on the dipole. Okay? Difference in the strength of electric fields divided by length into P. This gives me the force acting on the dipole. Under the influence of this force, dipole will move either towards left or towards right, depending on whether P is parallel to E or anti-parallel. Okay? If P is parallel to E, what I told, it moves towards strong field region. If P is anti-parallel to E, it moves towards weak field region. Okay? These are the things which you want to remember when the dipole is placed in non-uniform electric field. Okay? What are the formulas that we studied when dipole is placed in uniform electric field? These are the four important formula. For dipole, see, dipole placed in, I will write here just like, for a dipole placed in uniform electric field, for a dipole placed in uniform electric field, what is torque? Torque tau is given by P cross E, or it is P sin theta. should know how to calculate P cross E also. A cross D. Then second one, what is work done in rotating the dipole from theta 1 to theta 2? That is equal to P into cos theta 1 minus cos theta 2. Then third formula that we studied is change in potential energy. Change in potential energy U2 minus U1 is nothing but work done. This is also cos theta 1 minus cos theta 2. Then potential energy at a position theta. After considering theta is equal to 90 as a zero potential energy position, for any theta, potential energy is given by minus Pe cos theta. These are the four formulae you have to remember to solve some problems. Okay. This is torque. Then I also told you theta is equal to 0 position is called as stable equilibrium position. Stable equilibrium position. And theta is equal to 90 degree, theta is equal to 180 is called unstable equilibrium position. This is stable equilibrium position. This is unstable equilibrium position. Okay. These are the formulae for a dipole placed in uniform electric field. Make a note of this. We will solve some examples. Okay, that is. The simple question will start. An electric dipole of dipole moment P is placed in an uniform electric field E such that it is aligned in the direction of field. The amount of work done in rotating dipole through an angle of 180 degree is this is PE, this is P by 2. Simple expression, simple example it is. This is 2P Three P by 2, 3 by 2P. Dipole is already aligned in the direction of electric field. Okay? You pause the video and write the question. Then you listen the solution. Dipole is already aligned in the direction of the field. See, this is field. This is field. dipole is aligned in the direction of the field. This is P, this is E. That means it is at which position now? It is parallel to E, means it is at theta is equal to 0 position. From this theta is equal to 0 position, let us suppose it is theta 1, I should rotate it through 180 degree. That means I should make theta is equal to 180. That means from theta 1 is equal to 0 to theta 2 is equal to 180. What is the amount of work done, they are asking. It is very simple. What is the amount of work done? Work done formula you remember. Work done is equal to P into cos theta 1 minus cos theta 2. Here at theta 1 is 0 degree and my theta 2 is 180 degree. Then this W will be equal to P into cos 0 minus cos 180. Then this is P into E. Cos 0 is 1 minus cos 180 is minus 1. This already minus is there. Cos 180 is minus 1. Minus of minus 1 is plus 1. Answer is 2 into P. Follow this? Very simple example. Okay? Make a note of this. We will solve some more examples. Follow this. Let us see. Suppose if the dipole is displaced from a position through a small angle theta, if dipole is exhibiting simple harmonic motion. First you make it clear. Simple harmonic motion, what we studied in class 11th. Simple harmonic motion is of two types. One is called as linear SHM. Another is called as angular SHM. For linear SHM means the particle will be, suppose this is a rigid support, this is ground, and here we have some spring, here is a block which is displaced like this. And if it is oscillating like this along a straight line, then it is called as linear SHM. If you take the case of simple pendulum, if it is oscillating like this by making some angle theta with respect to this suspended position, with respect to vertical, this we call it as angular SHM. If the particle is vibrating along a straight line, it is linear SHM. If it is vibrating in this path, like this circular path, and making some angle with theta every time it rotates with the vertical, this we call it as angular SHM. In linear SHM, any particle, if it is executing linear SHM, then its linear acceleration will be minus omega square into x, where x is displacement, small displacement. This is displacement from, this is mean position. If you displace it through a distance x and release it, it will oscillate like this. X is called as what? Displacement. Here if I am displacing this simple pendulum like this, I am not displacing through distance x. I am displacing it through some small angle theta. Small angle theta. Then instead of taking linear acceleration, here we will take angular acceleration is equal to, this will be same, omega square, and in place of linear displacement we have angular displacement. Any body which is oscillating or executing simple harmonic motion, if it is linear SHM, it has to satisfy this condition. And here you remember what is omega? omega is 2 pi f, or it is also 2 pi by t. What is theta? Angular displacement. In linear SHM, linear acceleration is directly proportional to linear displacement, opposite to linear displacement. Minus sign shows that acceleration is opposite to displacement. In angular SHM, alpha is equal to minus theta. Angular acceleration is opposite to angular displacement, and it is proportional to angular displacement and opposite in direction. If I rotate the dipole like this through a small angle theta, its acceleration will be in this direction. This is the linear displacement I produced. This is oscillating back like this, like simple pendulum. If I rotate it like this through an angle theta, see, theta will be in one direction and its acceleration will be in the opposite direction, in proportional. Okay, if it is satisfying this condition, then it is executing. If a particle satisfies this condition, it is executing angular SHM. If it satisfies this condition, this will be linear SHM. Okay, remember this before I solve the next example. Okay. We will see this example. An electric dipole is situated in an electric field of uniform strength or uniform intensity E, whose dipole moment is P and moment of inertia is I. Stop. If the dipole is slightly displaced from its equilibrium position, just write like this, it is equilibrium. From its equilibrium position, then the angular velocity of the dipole, or I will take all, then find angular frequency or angular velocity. Angular velocity, that means it is omega. Or first we will write this. If it is slightly displaced from its original position, from its equilibrium position, first let us say, show that dipole performs SHM or angular SHM. Find its angular velocity and time period. Okay, now you see, first let us try to show that it performs SHM. It performs SHM means it should satisfy this condition. Alpha is equal to minus omega square theta, or alpha should be directly proportional to theta. See, in rotational motion we studied one more expression for torque, which is nothing but I into alpha. It is just like force is equal to, in rotational motion, this is F is equal to ma Newton second law. In rotational motion, torque will be force will be equal to torque. Force is just like equivalent quantity of force is torque. Mass is moment of inertia. Linear acceleration, angular acceleration. Tau is equal to I alpha. This also we studied. Now, if dipole is in equilibrium position in a uniform electric field like this, minus q plus q, stable equilibrium position, if it is rotated through a small angle theta, we have to show that it executes simple harmonic motion. That means, if it is rotated like this, see what is what I can write, what is the torque? That means I am going against torque here. Torque will be always trying to align the dipole in the direction of the field. I am going against torque. So what is torque? That is P into E, which will be acting in this direction. Then whatever angular displacement I produced, because of that angular acceleration, this torque will be equal to I into alpha 1 equation. And what is the torque that it brings back? What is restoring torque? Restoring torque is P into sine theta. See, I rotated like this, I produced this much torque. The force, the torque which it brings back is restoring, which will be opposite to this. Opposite, just like if I touch a spring like this by applied force, some restoring force will bring it back. Like that, this torque will be bringing that dipole in the direction of electric field. That means, for small values of theta, slightly displaced they told, for small values of theta, we know that sin theta is approximately equal to theta. If sin theta is approximately equal to theta, then what is this torque? This will be minus P into theta. This is second equation. If we equate these two, I alpha will be equal to minus P into theta. Then alpha is equal to minus P by I into theta. Now you see this is satisfying this condition. For simple angular SHM, alpha should be directly proportional to theta. Alpha is directly proportional to theta here. That means it is executing simple harmonic motion, which is nothing but angular SHM, which is if we equate this with respect to this, if we compare this equation, these equations, then in place of omega square, what is there? P by I. Then omega square is equal to, I can write P by I. Then I can write omega is equal to root of P by I. This is very simple. I have found out the velocity and calculated the angular velocity of this dipole. If I calculate angular velocity, calculating time period is not so difficult, because 2 pi by theta, I know omega is equal to 2 pi f, 2 pi by theta is equal to P by I. If you take reciprocal of this, then T by 2 pi will be equal to root of I by P. Then finally, what is time period? Time period is equal to 2 pi multiplied by I by P. Okay? Same question. We will take another example which is very similar. There we will calculate, suppose we will take both masses of both the charges. Then we will try to find moment of inertia in terms of mass. Okay? This you understood? First condition is it will show a SHM for this. Alpha is equal to minus something into theta. That will be equal to omega square. Then omega is equal to P by I. Then 2 pi by T is equal to P by I. So 2 pi by T, if I take reciprocal, this is still This very simple way I can calculate this. See, don't take t square, all those things. What is omega? 2 pi by t is equal to root of t by I. Take reciprocal, t by 2 pi is equal to root of I by pe. Then what is t is equal to 2 pi root of I by p. Okay, this is the time term. Now let us see. Same example you take. Okay, let's see. 2 point masses m each, having charges minus q and plus q, are connected by a massless rod, maybe in massless rod length. The rod through which these two masses are connected, let us imagine that it is massless, connected by a massless rod, massless, and I can say it is non-conducting, because charge should not flow through. Suppose if it is connected like this is the rod, this is minus q, this is plus q. This should be massless. Mass is here and here mass is here. Okay, but mass is not in the rod. Mass is situated at the ends. Non-conducting rod of length L. Okay. If this system will form a dipole. The system forms a dipole and is placed in an uniform electric field E. Okay, what is the length of this rod? It is L. If dipole is slightly displaced from its equilibrium position, then again you have to show that it executes SHL, and you have to find the time period in terms of mass and length. Okay, electric field applied here is E. Then how will you calculate the moment of inertia of this system? This is center, without adding. This is L by 2. This is also L by 2. Again I am telling you, this rod is massless. If rod is having certain mass, then I can write the moment of inertia of this rod as ml square by 12. They told that it is massless now. This is what we studied in moment of inertia. This rod is massless. It is just like, suppose for example I can say it is oxygen molecule. One oxygen is situated here, one oxygen situated here. It is bond. Mass is at the ends, not here. Can you imagine like this? Then how will you find the moment of inertia? Moment of inertia of this particle about this axis, moment of inertia of this particle about this axis. What is moment of inertia? Mass into distance square. Then what is moment of inertia of this particle? See, moment of inertia of this particle is mass into, what is the distance? Distance is L by 2 whole square. Then it is ml square by 4. What is the moment of inertia of this particle? This is I1, this is I2, which will be same L by 2 whole square, which is also equal to ml square by 4. Then the moment of inertia of this system will be ml square by 4 plus ml square by 4. Then moment of inertia will be ml square by 2. This is moment of inertia. After calculating moment of inertia, let us see here. Again, how to show that it's, what is the question? Show that dipole will perform SHM. Find its time period. Find its time period. Then what is this? This will be again same. I alpha is equal to P sin theta. In the last example what we had. Again for small angle, I alpha will be equal to, this is restoring torque, P into theta. Again alpha is equal to, what is alpha? Minus P by I into theta. Same expression we will get for time period as we solved in the previous example. What is that? Again this will be equal to omega square. What is omega? Omega will be equal to root of P by I. Then it is 2 pi by T is equal to this much. T by 2 pi is equal to root of I by P. Then T is equal to 2 pi root of I by P. This is time period. In the last example we calculated the same. Here in place of this, see, T is equal to 2 pi. In place of I should put ml square by 2. In place of P, see the total length is L, charge is Q. What is dipole moment? Dipole moment is equal to Q into distance, charge into distance, Q into L. So in place of this I will write Q into L. Okay, Q into L. Here I will write E. Then this time period will be 2 pi root of ml divided by 2Q into E. Understood? These are the few examples based on electric dipole placed in uniform electric field. Okay. In next video, if it is possible, we will solve some more examples or we will move to the next topic. Thank you.